Davis to you this evening. Her work crosses over fabrics and materials and performance, and essentially, right now, just to give you a little basic back information, she currently teaches at the Stuckeman Center for Design and Computing in the School of Architecture and Landscape Architecture at Pennsylvania State University, and she's the director of something called SOFTLAB, which I think we're maybe going to learn something about there, and she received, I'm going to give you the data, her background. She received her master's in architecture from Princeton and her Bachelor of Science in engineering. So that's interesting, the engineering part, from Tufts. So here's where it gets super interesting, I think, is where she has a PhD now in the Design and Computation Group in the School of Architecture and Planning at MIT. And her dissertation, which she will be publishing with ACTAR in this year, next year, borderline, entitled Soft-Built Computational Textile Architectures, researched and developed computational textiles that respond to commands through computer programming, electronics, and sensors for use in architecture. So in this world that we're all in, where we use things like BIM, right? BIM, horrible that it is, but it exists, files, where we can extract or exchange or network support decision-making regarding buildings or other built assets. And these computational models are really embedded with various types of information into our drawings and our construction documents. So I think what she's doing with computational materiality is just an incredible expansion of that, working to explore materials that are responsible and self-actuating and embedding information into physical material. So I look forward to discussion and questions with her afterwards, which I hope you'll all join me with. So Felecia Davis, thank you.
Thank you, Laurie, for the introduction. It's really nice to be back here and also to see some of my former students from Penn State now in a new environment and learning new things. And I'm very excited to be invited here to share some of the work that I've done in SOFTLAB at Penn State in the Stuckeman Center for Design Computing. Now, SOFTLAB really started about 5 years ago, and I should add SOFTLAB at PSU because there is another SOFTLAB. And SOFTLAB, as the lab that I run, it is really looking at the ways in which computational textiles and architectural design kind of intersect. So within that, there's a kind of huge, I would say huge numbers of questions that we're looking at to frame and answer. And it's a lab where I work with both undergraduate students and graduate students, and we're both learning from each other. Teachers are learning from the students are learning from each other, undergrads from grads from undergrads. So it's been a very exciting place to be. So today I'm going to present some works from SOFTLAB, as well as works that I did as a PhD student at MIT, and really are forming the kind of body of the book that I'm currently working on. I'm going to present two theoretical ideas that originate with Semper and guide the kind of bulk of the research that we do at SOFTLAB. And as you know, if you're in architecture, Gottfried Semper was an Austrian architect and designer writing in 1851. And he's basically trying to figure out how to organize crafts, all these different types of things that he's seeing at the Great Exhibition of 1851. And he wants to kind of make sense of all this stuff for people who are craftspeople, people who make things for buildings, people who make buildings, people who make ceramics and sort of glassware. So he uses architecture and begins to figure out a way of kind of organizing the cacophony of what he's seeing at the Great Exhibition. So he does this in his book called The Four Elements of Architecture, and he uses architecture to set up 4 different ways of thinking about crafts. For example, in his book, he designates hearth, as relating to fire and ceramics. He uses the roof of architecture to talk about carpentry. He uses the enclosure of architecture to talk about weaving. And he uses the mound of architecture to talk about stone masonry. So most of this is familiar to you guys if you've done some undergraduate work in architecture. And what you're looking at is an image of the hut from Trinidad, which was on display at the Great Exhibition in 1851 in London, which inspired Semper to come up with his 4 elements. And you can see a base, you can see the structural columns holding up and making the roof, which was then covered with a lightweight woven enclosure. And Semper's most effluent, he's really excited about weaving, which had to do with the idea of enclosure. And for him, there were 2 main problems to resolve if one's going to construct architectures with soft material. The first is structure, which Semper, primarily interested in anthropology, doesn't really develop as a primary focus. For him, the structure was necessary to hold up the walls, but it wasn't where it wasn't the thing that floated his boat. So the second issue, and his principal concern, is that of communication by the textile wall or its social emotional function. This wall renders the concept of an interior life present and seen as separate and distinct from the exterior or public life. So this is the first idea I'd like to highlight for you in my work, and it's something that I begin to carry forward computationally. In the next 20 years, research work in lightweight architectural building materials using textiles will include computational textiles, which are textiles that respond to commands from sensors, microcontrollers, and other electronics, in addition to transformations of natural materials. So as we begin, as architects and designers, to understand what these materials can do, they'll more and more have the ability to inflect how we live our daily lives, and they're doing so already, affecting social, spatial relations, emotional effect. So the second idea I'd like to present to you through my work is Semper's link, or as he states, the correlation of architectural enclosure with clothing. You can see here in the 2 images from Semper's book, The 4 Elements, which show an Egyptian lotus column on the left-hand side of the screen that is bound at the top, the flower is bound at the top with a kind of cord. And on the opposite side of the screen, you can see hair decorations of Egyptian women with dreadlocks that is holding a kind of scented oil piece on top of their head and using the kind of idea of the cord to bind it. So that there's this crossover between architectural elements, architectural building, and clothing, really connecting through this idea of style. So Mulgrave, writing about Semper in 1989, notes that the German word for wall, Wand, is linked to the word Gewand or dress, thereby proposing an explicit connection between the concept of architectural enclosure and the concept of clothing. So this is a second idea that we have categorized the kind of research work in SOFTLAB. So let's talk for a moment about what I mean by computational textiles as a material. If you really start to think about it, computational textiles change the idea of a material. A material may be seen, like the above image, as a person or body, a body monitor, such as a heart monitor, a mobile phone, a laptop, a set of responsive yarns or fabrics, a power system, and larger, the environment. So going back to Semper really begs the question, what style of material do we have here? What kind of skills and tools and resources are needed to create such material? How should we classify and describe these materials? If materials change us as we change them, what is that doing to us? Tim Imgold and J.J. Gibson and many others argue how these materials are changing our body. And they ask, how are they changing our way of thinking and living? So I'll leave this question open for us to come back to and think about at the end of the lecture. So I'd like to talk to you for a few minutes about one of the first of, I think, 7 projects that I'm going to show you, 2 of which are unbuilt architectural projects, and the rest are rather prototypes or computational textile projects. So this all started with a thesis project way back in Princeton with the African burial ground, which was happening around 1991. It's in Lower Manhattan. Many of you could go take the train down there and visit. But this project propelled me to look more closely about the relationship between architecture and textiles. And it soon became something on my brain. And I thought I was done with this project, but then after I finished my PhD, I looked back and saw that it wasn't done with me. So as you know, the burial ground was unearthed while digging the foundations for a 34-story federal office tower at the corners of Duane Street and Lower Broadway. And I came across, doing some research for burial customs in Western Africa, came across this photograph in African Arts Journal and was really struck with this. What we're looking at is a scene of women who've prepared a burial bed and displaying all the sort of intricately folded and twisted cloths as part of the burial ceremony. These are Kalabari women. So the project for a burial ground was, in the case of my thesis, a project about recovering sacred grounds using cloth to cover up something that maybe shouldn't be seen scientifically, and uncovering it and allowing it to be seen so that one could learn more about the people that were buried there. So both accommodating architectural or archaeological cataloging as well as reclaiming sacredness. And these are just some examples from the Kalabari, elaborate folding and kind of display of the cloths on the burial bed. The project that you're looking at here is in this corner. There was the thesis project. And it's a series of folded and patterned glass planes, accommodating both the museum and sacred space. And essentially led me to designing this fabric itself, getting into thinking about what the experiences I wanted the people who were going through this project to have. So the details of the glass were generated from the strong directionality of bodies laid in the ground and African patterning. So colorful cloth that you saw in the picture, I began to think about differently because it was coming to me from these kind of technological, Xeroxes I was using at the time. I don't even know if you guys know what a Xerox is. Maybe you scan everything now. But I was using Xeroxes, and we didn't have color Xeroxes. You had to cut it out with scissors, tape, and paper. So that really changed how I received it, and I began to sort of register that through the color of this cloth as well, which you can see the color is removed. So all the other projects that I'm going to show you are inspired by research from this beginning project. So the first computational textile project I'm going to show you is an exhibition I did with a friend, Delia Dumitrescu, now the director of the Smart Textiles Lab at the Swedish School of Textiles in Borås, Sweden. It's called Patterning by Heat, the Responsive Textile Structures, and was exhibited at MIT Gallery at the School of Architecture in 2012. This exhibit included 4 tubular computational textile tension structures, which were about 8 feet tall by 3 feet in width, and each tube featured one of 2 material responses, which were activated by an electrical current triggered by a proximity sensor. This current irreversibly changed the pattern and surface appearance of the material. So These 4 tubes were designed in Sweden at the Swedish School of Textiles on their industrial equipment. And they were designed with patterns that either closed or opened the fabric, knitted with yarns like polyester, cotton, monofilament, which is like a fishing lure, copper-coated conductive yarns, stainless steel yarns, very, very thin, steel-coated yarns. And you can see that there was a big difference between being up close and being far away from one of these tubes. So as we started to work on our designs, we really had to proceed at 2 different scales, the scale of the overall tube and at the scale of the individual geometry. On the right side is what we use to communicate to the master knitting technician, which is called the geometry of the stitch or binding structure. That's the most important drawing, the binding structure for the knitting technician, and how the machine actually reads what instructions you give it. So the stitch geometry, along with the combination of yarns, gave the fabric its overall character. So as we started to work, we began a series of sketches, and I call these things that, they're sort of, we would knit a small piece and then try something out. So on the left, we were trying out grill-on yarn, which is a melting yarn. It opens at about 140 degrees F. And the material structure, we tried to make a kind of more neutral structure that so that other designers could come in and make their own pattern. On the right-hand side of the slide, you see us using a yarn called Pamatex yarn, which was used to close the textile by shrinking up to 40%, which is about 194 degrees Fahrenheit, by current running through it, which are knitted, it's knitted together with conductive yarns, which you can see in the darker areas on the slide on the right. So once you heat that up, you get these kind of more opaque areas. So each of these tubes took several tries to select a pleasing combination of yarns, yarns that actually would work in the machine instead of snarling up and kind of getting stuck. And some of the preliminary fabrics, just a few, fell apart or snarled, but we had a great deal of help with the master knitting technician, who really had a great sense of what could work, what could not work, because obviously this person had been working for over 20 years with these different materials. So that saved us a lot of time. Some of the tubes were knitted as a whole pattern, which was a shape inside a shape, so knitted on a machine that knitted sleeves or something like gloves. And other tubes were knitted on a kind of more straightforward, you put it through a kind of circular machine and it comes out the other side, like this one that you can see knitted with steel. This is the knitting laboratory at the Swedish School of Textiles where the tubes were made. And as you can see, there are a lot of samples of clothing, there are a whole bunch of knit samples, there's a whole bunch of stuff around. And the stuff is absolutely critical to making something. Just like in architecture, we have precedents, we look at things that other architects have done, we begin to make models to get a sense of how they actually work. This was like that for a school of textiles. So, you can see that kind of stripy thing at the front. You can look at the structure, you could start pulling on it, try to understand how the yarn was working. You could take the geometry from it and then begin to invent from there. So we weren't starting from scratch. We actually had an incredible library of stuff that was like all around us to figure out like what we were doing. And so what we wanted to do, we knew we wanted to do something with tubes, and we started with this sample. This was a sample hanging up on one of those racks that I just showed you, and tried to figure out if we could make tubes that joined or tubes within tubes. So we started fairly simple just to begin to understand. These particular precedents or samples were made on what we call a whole garment knitter, where it makes socks, it makes pants, it makes your kind of sleeveless, your seamless sleeve for a sweater, and you could join different tubes together so you could get some really interesting architectural shapes with it. So this was our kind of precedent for that in the lab. And we made several different samples. You can see some of them lying up front here in the foreground. You start with using really cheap yarn in the machine because the machine gobbles up huge amounts of yarn when you start. It's unbelievable how much those things eat up just kind of like getting started. But we made a few different samples, got some to work, and this is Christian Rodby, who was working with us, the knitting technician, and we're putting our stitches in the program for this machine, which is the whole garment knitter, which looks like that. Looks like an architectural printer. It's very small. It doesn't make a lot of noise, and the yarn kind of comes in and spews out the front. So that was one machine that we used for the tubes. And a second machine that we use for the tubes is on near screen here, left side for you, I think. It was basically a circular knitting machine, and with that knitting machine, you could only work with a kind of constant diameter. So you couldn't do the kind of variegated diameter that you could on a smaller whole garment machine, but it knitted really fast, and it could also take in much stiffer yarns. So you can see the material coming out on the left-hand side, and then its feed, you know, on the right-hand side where we were changing the yarns and kind of mixing it up and trying different things to understand what was going on with our material. So just to go into detail, just to show you two of the tubes, one opening tube, one closing tube. The first one is Pixelated Reveal, which essentially used the grill-on yarn, which is the opening yarn. We had 5 courses or 5 stitches that made these kind of series of pixels through the fabric. On the left-hand side of the slide, you can see the image is, the fabric is closed, and on the right-hand side, we've introduced a current that opens these kind of pixels only where you have that yarn. So you can see it's in there as a pattern. And the snaps are what we use to introduce a current into it, a positive and negative side. So the idea with the pixels was that, you know, you could give the fabric over to designers in general and let them pick where they wanted to put the snaps so they could pull up their own pattern. So it wasn't, we weren't just making it for us, we were trying to allow other people to experiment with it. And at the scale of the tube, we began to see that, you know, it was really complicated to see these little tiny samples that we were making in kind of its totality. So we began to make a series of drawings that would help us understand the temporality and the way in which the material would be connected. So we invented what we called these choreographic drawings, where we unfolded the lengths of the tube and then drew out what we wanted to have happen. In this particular case, in Pixelated Reveal, we have a spiral going from left to right and right to left, spiraling up and down. And the spiral going from left to right, top to bottom, are much shorter. We timed those and got a kind of reaction rate of 8 seconds, and going the other way, about 40 seconds for the longer ones. So we were trying to figure out how much time these things would take in terms of how they could react. And we also used a drawing like this to figure out how it could connect to a microcontroller, how it would connect to the sensor we were talking about, and how it would connect to power. So this was the way that we kind of figured out how to map everything together. In spite of the drawing and in spite of our organization, it took a huge amount of time counting. So, you know, at the end of the day, we had all these computational, we had all this programming and stuff we were doing to get the power to run, et cetera. But at the end of the day, we were literally counting by hand the pixels going across the fabric and sewing and basting in where we wanted our pattern to be. So if one were to figure out ways of reducing labor, and textile manufacturing design is notorious for being labor intensive, this is something that we need to work on. So it took a couple days to sew the pattern on and to connect the snaps in the right places. And then by the time we got the snaps on, it was a huge tangle of wires inside, like a jellyfish coming down in the middle. But I have a video for you to show you the reaction. In between, you can see the positive and negative leads. And it's been slowed down a lot. So this video is about 40 seconds long, so you can see it. This is another thing we learned, that you know, you need to give time for these things to happen, for people to perceive them. But in fact, actually what we're looking at is something that is 8 seconds. So if you're walking by, it's really hard to read it. But the idea was, over time, numbers of these would open up, and you could begin to see the kind of disintegration of this tube as well as its elongation. So that was a pixelated reveal. And let's see. The second tube that I'll talk to you briefly about is called the Radiant Daisy. And the Radiant Daisy is made with the closing or shrinking yarn, the Pematex. And it was really much more difficult than the pixelated reveal. Even though the knit is much simpler, you can see it's basically conductive yarn going around the tube. That simplicity actually turned out to be more complex, because if you want to run and control current, you have to snip the pattern out to disconnect positive from negative around the pattern that you want. So we tried this daisy, and we discovered in our samples that we could get the samples to work, but it was really tricky getting the whole thing to work, and we couldn't figure out why. We were like, works here, why isn't it working up there? What's the problem? It turns out that when we hung the fabric stretched and introduced resistance into the pattern. So all of these things, I don't know if my arrow is going to show up there, but all of the dark kind of sewing lines that are making the patterns, that's conductive yarn. And these dark horizontal lines, that's conductive yarn knitted into the tube itself. And so what's happening is the tube is stretching and stretching and driving up how much current we have to pass through it to get it to run. And so ultimately we had like a pfft, and the thing burned a hole into it. So that's another thing about computational textiles that we learn, is that, you know, tension, when you put something in tension, obviously you're gonna change the resistance, and you need to be able to calculate that. Of course, you can't calculate that unless you figure out what's going on with the fabric, but it was a learning experience. So here's our choreographic drawing for the Radiant Daisy, and the daisy was meant to open counterclockwise, 1 to 11, running positive and negative at the top and bottom of each petal. And again, it worked at the sample level. If you can see in between the dashed lines, you'll see where it's basically shrinking and making that area more opaque. But once you hung it up, we had the resistance, and so we couldn't get the daisy to work. And this is some more samples where we got it to work. It's very subtle, but again, there was a big, huge difference from our samples that laid on the table and samples that were out in space. So this second computational textile project that I'm going to talk to you about was inspired by J.G. Ballard's short story titled 1,000 Dreams of Stella Vista, which is about a house that is made of psychotropic material. It's material that could potentially read your mood. That's the kind of narrative of the fiction. And so the house in the story affected the emotions of its inhabitants. If the occupants were happy, the house formed swooping, curvilinear shapes and smooth, peaceful shapes. If the inhabitants of the house were unhappy, the house drooped with sadness or became taut with rage. So this house is kind of in conversation with the material that it's made out of. And the project was done in collaboration with colleagues at Microsoft Research, and was really looking for ways to make devices, create devices that could allow people to become aware of their emotional state. So while this was one project within the team, there were a couple others going on as well, but everybody was coming together to look for how, objects can begin to make people aware of their emotional state. So the textile mirror uses a smartphone that's networked to the textile so that an emotional reading can be selected by a person. This reading is fed to the textile, and the textile responds. To start to understand what emotions were communicated by different textures, we did a visual survey of textures on Amazon's Mechanical Turk, which is its crowdsourcing website. We got back really consistent results from Amazon's Mechanical Turk. However, as it turns out later in my dissertation, because this is fairly at the beginning, it turns out that these results are only true and consistent for photographs. In other words, if you tell lots of people to look at photographs of something lit in a certain way from a certain angle, they will understand something is scary. They will understand something looks happy. They will understand something is joyous. But as soon as you take that one kind of set lighting and set kind of positioning away, people can turn their heads, they can move their eyes, and if you let them touch things, that's a whole nother world. So as soon as you're live with something, it changes all the emotional responses. So there's something really interesting about photographs, I don't know, and images that's very different from live stuff. So that said, the idea here is that when the textile is crumpled up, it's communicating stress, which you can see on the right side, and that state is trying to communicate to someone to make a person aware of that stress. So the way that we were getting the textile to actuate became a really important part of the study because it actually gave warmth to the project, and I'll explain. What we're doing here is molding nitinol, and we're shaping the nitinol wire around a steel mold that will not melt at 500 degrees C or about 1,000 degrees Fahrenheit. So we took the wire and made our shape with it, and then once that was done, it went into an oven, this kind of prehistoric looking oven, which is a glass firing oven, and put that in there. And when you put that in there and take it out, you can pull the wire straight, and as soon as you run current through it, it will take the molded shape that it had in the oven. So we were using that as a way to make or help the fabric open and close in the video, and it took a few different tries. Here, once we discovered we had to run a lot of current, through the nitinol to get it to work, we knew we had to cover it because we wanted people to look at it and also touch it. and we didn't want people getting hurt. So we ended up trying a few different things. We tried Kapton tape, which is this kind of yellow tape, which is a heat-resistant tape to coat the wires in the back. It turned out that the Kapton didn't allow us to have enough crunch or folding. And we took off the Kapton and just went with the kind of the shrink wrap, and that seemed to work to give us an actuated piece. And then once again, just hours of labor sewing on these pieces of nitinol to the work that people then could touch on the front. And when they touched it, in our studies, they mentioned the warmth coming from the wire. So it did have an effect. When you touched it, you felt the kind of warmth, and it was a pleasant warmth. It wasn't like, ouch, or, something that was uncomfortable. But it did transform what people took away from this and how they understood the piece. And then we were thinking about potential applications. Some of the participants in this study were talking to us at the end of the study and said, you should use that at the dentist's office, because when you can't talk, it would be really nice to tell the dentist that you're stressing out and you want to communicate that somehow, and they're not listening, or they're just talking over you, not really looking at you. And so this was one of the ideas that we drew up. Another was thinking about what happens when this isn't necessarily just a one-to-one relationship. In the video, we have a one-to-one relationship. We have one person picking out an emotion, and then the cloth reacting and showing that emotion. But in this case, what if it was a group of people? And thinking about that, it took us to the whole question of privacy. You have to wear sensors to have this happen, or you have to have cameras, and those cameras have to feed information somewhere else. So I think both of these projects raise issues about privacy and where your data goes and who's reading it for what purposes. So this is just a hallway in our school. So that is something that we are also thinking about in SOFTLAB. So a second computational project, or third computational project I'd like to share with you, is called FELT. And it too is a study that was developing some of the things that we learned from the textile mirror to more fully understand the relationship of vision, touch, and emotion. As I said, when we allowed people to touch the textile mirror, it really changed the reactions. We weren't originally planning it, but then someone didn't touch it, and then they were like really, it changed what we thought were going to be the responses. So this project is a follow-up to that. And the design for felt was a kind of refinement of the preliminary studies that we did for the textile mirror. This was inspired by animal reactions, some of which Darwin mentions in his book, The Expression of the Emotions in Man and Animals, which is written way back in 1872. He doesn't say that, when you see an animal, a cat with their hair kind of like freaking out, or a bird with their feathers ruffled, he doesn't say that this cat or this bird is communicating explicitly to you their fear, but we can infer that. So as a designer, this is something that I wanted to use to communicate, not just infer, but to communicate to people a particular emotion based on these animals. So I was trying to be really explicit without using words, and also trying to get away from photographs because of what we learned from the first project. So it was expected, I was expecting that the movement of each animal's skin, fur, or feathers would communicate or permit a person to infer a different emotion using their vision alone, and then using vision and touch together. So I came up with a series of different small panels. These are about, the actual pieces are made out of felt. They're about 9 inches by 9 inches, and they were echoing some of the things that I had seen in Darwin's book. There are some beautiful drawings, as well as some of the sketches that I had done of those. So the one in the far left was really trying to, emulate a kind of tension. And the one on second one in was kind of unfurling, more tentative thing. The piece in the middle is what we ended up going with, because after asking many people about the emotions they thought were communicated, that particular texture elicited really varied responses. On the one hand, people really loved it. It had a lot of kind of tactility. On the other hand, people thought it was obscene and hated it. So we have these vastly different responses to that one in the middle, and I thought, hey, that's one that would be worthwhile studying some more to see what would happen. So felt is taking that middle texture and enlarging it to see the effect of the scale change, but also to understand more about this particular texture. So this is about a 5-foot wide by 6-foot tall piece, modular panel, that was designed to explore how using vision and touch together changed one's emotional responses to the texture. The piece also moved. So I don't know if I explained that in the first, in the little kind of sketches, but there were a series of motors behind the piece, or at the top of the piece. You can see maybe in the third from the left, there's a series of little motors that are pulling a 2-layer fabric panel piece up and down. So these fingers moved up and down, and you could hear these servo motors going on in the back, and that was also a factor that people mentioned in the study. And again, sewing the pieces onto a kind of aluminum frame, getting them to be kind of stable enough. And you can see on one side you have these kind of fingers fairly finished, on the other side this very elaborate kind of wiring that's going on that's actuating the piece. So again, this project was done with a team of students. I had help because it was very labor intensive. If I tried to do this myself, it would probably take me 6 months in between my normal teaching responsibilities to do, but we did this probably over a couple of months in the summer. So one of the things that came from this are different ways of touching. People in the study really touch this in very different ways. They use pinch, they use kind of stroking with the front of their hands, with the back of their hands, and each way that they touched it changed what they felt was communicated. So there was this really interesting feedback loop. What we thought was communicated was really something that transformed over time. In other words, as people touched it, they got new feedback. It changed them, and they changed it. So touch is this kind of two-way sense that we have, that it isn't just one way you touch it and you get a reaction back. You're constantly changing what's happening. So some people, really wanted to get in there and put their whole bodies in the study on it as much as they could, but it being panelized, it was hard for them to get the full effect of their entire lengths and their legs on that. So a continuing interest from this project is to understand more about how touch can be used to communicate with people as a nonverbal language. And you might ask, why would someone want to do this? Well, many people don't have access to their emotions. They have difficulty talking, but if they feel something that can elicit words and kind of free them up to be able to communicate with other people. So in combination with sensing capacity, I have some samples up here for people to look at afterwards. This particular example on the slide is made with resistive yarn, and when you pull it and you connect it to a microcontroller, it senses the change in resistance, and you can use it to talk about someone's breathing rate, or you can use it to maybe talk about someone's stress if they pull something. So there are many different potentials that can happen When thinking about these fabrics, this particular one is made with a highly conductive yarn, and if you put two of these together, put two of these fingers together, you can kind of make a series of pinches that change a series of signals from the fabric. So who knows, maybe instead of using a keyboard, we could use pinching or begin to pull at fabric to communicate different things. So this project is a project that I did with students last spring. It's part of a competition that we were invited to participate in. The competition was sponsored by the American Composite Manufacturers Association, who provided resins, fabric materials, and expertise for the competition. The competition is really looking at how to innovate with fiber composites, lightweight fiber composites. So our team was inspired by colleagues' work using origami and fiber composites, and it was also an opportunity to return to the folded plate structure that had started with the African burial ground. So really looking back to that as a source for thinking about how we might make compressive structures that could also be flexible. So it's a day-night pavilion or day-night kind of shading that we looked at installing in one of the hallways at school, and very interested in how origami could allow us to make different shapes so that the space, you could start off one way and you could push it down or pull it apart and kind of fold it and get it to do different things. So we were really super interested in how something that could take compression that was very hard, like a fiberglass with resin in it, and it could be this kind of malleable material. So we came up with this kind of folded fan shape that would partially shield the hallway during the day, blocking the sunlight out during the day, and at night we wanted to connect it to motors so that it would open. And you could basically let the light in. Well, we got into a whole bunch of other things as we moved through this, and discovered that the fabric that we had been given was this kind of knitted textile, and became very curious about how we could introduce other functionality into this kind of very basic knitted fiberglass fabric, and introduced electronics in it so that when the piece was up at night, you could have a kind of light background lighting aspect to it. So really this was a series of experiments for us. We had a lot of fun doing it. It happened very quickly, and I can show you just some of the images from our production. There's the piece at night. It's got this really nice translucent quality to the piece, so that the light does still come through, but you could also introduce this kind of conductive fiber to it, so that at night you could get these little tiny kind of starlight LEDs in there. Production was moldless. It did not use a mold, so we essentially made a template that went on top of the knitted fabric, and then rolled our resin on top of the fiberglass. We tried this a couple different ways. The first ways, we tried a couple different fabrics. It didn't, work immediately, but finally we landed on this knitted fabric that we really liked and went with. We also made a kind of placement mold, not really a mold. We're not using it like a mold, but we're rather using it as a kind of system of measure to get the pattern onto large sheets of this fabric. I think the sheets of fabric were 12 feet by like 3 feet, so they were quite long. You had to kind of get that going. And these are our first tries with it, using a woven toe on the left, so much thicker fabric, and then what that looks like. And we tried the knit after receiving samples from our sponsor, and decided we really liked that, and went with that. So what you're looking at is just the whole fabric laid out with tape on top. It's all resined up, sitting on top of waxed foil, and you can just easily peel it up when it's done. It takes about maybe 15 hours to cure properly. It gets quite hot with the resins that we were given. And this is our circuit drawing for the LEDs that we introduced. We sewed these on the parts of the fabric that were not resined, because as soon as you resin something that's conductive, it closes all the spaces in between the fibers and it can't conduct the electricity. And there we are sewing away, a close-up really of what it looked like. We think that this would be, obviously, if one could do this ahead of time, you could have a really beautiful fabric that could carry different electricity and give you some background lighting. It could also potentially do other things as well. So while our sewing looks very crude here, we think that you could actually go to the mill and introduce these conductive yarns into this fabric fairly easily. And then just keeping track of what happens when you fold conductive yarns, because suddenly what's positive and negative are coming into contact with one another. We wanted to make sure that we had a wide enough space, and that did not happen, to short the piece out. We also thought about, once you open and close it, maybe we could use shorting actually to become a switch to open and close the light on the piece as well. So we learned a lot from this. Even though it didn't work in the way in which we originally expected it, we learned a lot from this and have other plans for what to work on next with this. So I'm going to shift gears here and show you an early project that relates to landscape and architecture. It's a more conventional architectural proposal for a history museum in Fresno. It was a competition project that we did where we were picked out of finalists and given money to continue our second phase of the competition. And it basically was located in downtown Fresno, which you can see there. And we were interested in how we could frame the idea of history through materials in the landscape. So we were really very wanting to bring those materials, that kind of tactility of stuff, into the building. So the idea started with the meaning of Fresno, or ash tree in Spanish, which is fraxinus in Latin. And the building was conceived of as a frame which used the surrounding, kind of flora and fauna as the literal walls, not the fauna, but the flora, which enclosed the space of the museum. So the surfaces of this building became the way in which we thought about history and how this building was connected with the landscape. And we made 5 kind of interventions through the building in 5 places. Each of the 5 surfaces communicated a story of this place. And as you can see, our project is a courtyard scheme that's located in downtown Fresno, across from which is an empty parking lot. We wanted to have a kind of continuous diagonal through the building because there was a very big and kind of ongoing farmers market that we knew was only temporary, but we wanted to preserve the porosity of this place to make sure that farmers market was still going to be fed. So this is the front entrance to our building, which had a projection screen in the front, which is meant to show movies or current events that were happening at the time. And basically the entrance is facing opposite another museum, the Fresno Art Museum, and it's rotated off the main drag. This is the elevation on the main drag, so that these 2 museums could communicate, because we're interested in really connecting along the smaller kind of alleyways or the smaller pathways in the town. So we chose to locate our entrance at the corner where you had this kind of less ceremonial street, but still obviously it was easily accessible. The second surface landscape I don't know if I told you about the first surface. The first surface landscape is this ash wood, which was pressed in between glass, making a kind of pressed glass curtain wall with the ash wood, very, very thin veneer, was translucent in some places. And the second surface landscape is this courtyard area, which you can see in the first floor plan on the left. And that courtyard held the layout of an edible and local produce gardens and a French garden plan. There was also a large high pool of water that fed a system of irrigation trenches in the ground, which fed the crop plantings. And inside you entered on the diagonal, and there's a view out to the courtyard that I explained to you about that had the farmer's market. And the second floor plan on the right was an out-of-door porch area that was the third surface landscape of cultivated mowed grass lawns that dotted the suburbs flaring out from the center of town. So this image shows a rendering of that courtyard along the diagonal view out to the farmer's market. And again, we were trying to get it to be very porous and kind of make a screen area where you could also project images on. So this surface of this building had lots of projection. It had the kind of stuff of the landscape that was embedded into it, the ash wood. And the last the fourth surface landscape, which faced the courtyard, was a vertical growing wall, and it featured plantings from the desert and uncultivated parts of Fresno. And while we were trying to develop our ideas for these landscapes, we began to look at ways to show the artificiality in the ways in which farmers were growing things around Fresno, which is really the fruit basket of the United States. So we were trying to emphasize this kind of artificiality in some of the sketches and designs for these growing walls, etc. We were very inspired by Chuck Close's work with pixelations of a surface that explored the transformation of these artificial live surfaces with supplements that would change their rate of growth to bring attention to how these things were being grown. So this is pictures of the model day and evening where you got this kind of translucency through the ash wood that you can see at the bottom. The last project that I would like to share with you returns to Semper's ideas of using clothing as a way to think about architecture. So this is a collaborative project that's done with Conrad Tucker's lab, Data Lab, at the Department of Engineering, Design, Electrical Engineering and Computer Science at Penn State, and Delia Dumitrescu at the Swedish School of Textiles. The purpose of the project is to measure the position and pattern of a person's legs in space. So if we can do this, we can detect the patterns of walking and help identify diseases early on, such as Parkinson's disease, as well as help prevent falls in older people. But I have to say, we started this project from architecture, really trying to understand, well, what can we understand about bodies in space, and what can we do with that as architects? So in this case, you're looking at a wearable or pair of leggings whose purpose is to measure the position and pattern of a person's legs. And if we can do this, as I said, we can potentially figure out what if someone has Parkinson's, when they're going to fall, etc. So this is our first prototype. You can see it's got some things that you might recognize. I know a lot of this is ongoing in architecture studios now. You can see a lily pad, an XB wireless device, also conductive fabric that's been sewn into a pattern, a battery holder, and some other kind of electronic bits that we're using to collect data. The thing that we tried to do with this project was move away from a camera-based system where a person must be located in a room and tied to a camera. So what we were trying to do was make all the sensors, or put all the sensors on the person so that you could track the position of their legs and that they could be free to walk the dog down the street or make a quick run for groceries. So we were really trying to update some of the research that Conrad Tucker had done using a Connect sensor, which basically beams light at you so that you can tell the distance between it and the person. But you need to be stable more or less in a space to do that. So we started out looking at how the human body works because we knew we were wanting to locate sensors on the body, and came across these photographs and also some really nice drawings by Paul Webb, who is an engineer and designer who designed the elastic leotard, which he calls the Apollo spacesuits, way back in the early 60s. And so what he was trying to figure out is where your body extends or stretches the least and where it stretches the most, so that you could begin to use that to figure out how to get this spacesuit to operate. And of course, they're working with gas. They're trying to pressurize the spacesuit to keep the human body from exploding in a vacuum. You got to pressurize it. And so they're trying to figure out like where you can allow bend to happen with all this gas around you. And recently, of course, Dava Newman has been working with lines of non-extension. Oh, I don't have a picture here. To show that maybe we don't need to use gas to, compress people. We can use these lines with nitinol wire. So the nitinol can contract and to provide this kind of pressure, getting rid of the kind of cumbersome gas which goes around your arm. And we began to use and look at where the skin moves to locate our sensors. So this is us in SOFTLAB, a couple of my grad students, trying to figure out where the sensors should go to get the best reading, and then testing it a couple different times, actually, more than a couple different times. We had, I would say, models that looked like the ones I just showed you, and we also now have ones that are industrially knitted. This one is waiting, this particular prototype is waiting to receive its sensors so that we can see how these conductive yarns work, and if we're going to get a clean enough signal back to be able to tell the position of a person's legs, which we could in our previous models. So with that said, in closing, the contributions to architecture made by computational textiles is cultural, social, and technical. These materials change how we think about architecture, and I think propose some interesting questions for the future. And with that, I would like to close this presentation and take questions from the floor. Thank you.
I was thinking about scaling and how you might scale what you're working on. It's interesting that the final project came inward and came to the body, actually, so it was clothing, like not even the industrial design, but back to actually the body itself.
Yeah.
So it was getting smaller. But I kept thinking about the potential, or what you might think about the potential when I think about Friato, or I think about some of Shigeru Ban's structures using paper tube, even though he's using it with a kind of glue, something that hardens the paper, which is almost like a kind of pressed felt fabric. Is a similar kind of process. So, the origami obviously has structural implications with its scale, but so I was curious about how you thought, or
Scaling up.
How you thought about scaling up.
Yeah.
Scaling up.
Yeah, I think it's a good question, because a lot of times we have been working with smaller samples because it's what you do. It's a lot easier. It's cost effective. But in terms of scaling up, I think the work with the fiber composite was very interesting this spring, because I think that is the way to go in terms of scaling up. At the beginning, I'm interested in introducing these other potentials for communication through it, and so would be really interested in working with textile mill to make a fabric that would be at scale, that you could then do a series of fiber composite pieces that are larger and successively get larger. One of the things that I have learned over the years by doing this is that scaling up comes step by step. Like, I would never just go from a piece that you saw in the presentation and then try to make something giant. Like,
Right.
it's kind of small steps at a time, because at each step you're figuring out problems of how to get it to work, how to get it to work at the next scale, how to get it to work at the next scale. So, yeah.
But it's interesting that in working at the scale of weaving and fabric and piecing together, like you're piecing clothing together, that it does have a relationship to this other scale. I think of Peter Testa's carbon fiber tower, which is something that's woven. I don't know if people are familiar with that, but it's a huge structure, and because of the composite material that you're now looking at, you have the potential for this strength that works in both tension and compression, right?
Yes.
It's very successful. It's incredibly light. I mean, we want to, if Bucky Fuller, if you want to, like, how much does your building weigh? How do we think about going into the 21st century? Can we be lighter in all kinds of ways? So, I mean, I think I'm just really curious about that potential. So that's kind of.
Yeah, actually, the other day, my husband was showing me an image of Apple's new theater project that has this huge carbon fiber disc roof. It's really beautiful. It's kind of perfect circle, and I think it bows in a little bit. And they were able to cut the weight of that down by a lot. I'm not sure the magnitude, but it was worth it in terms of the savings. So yes, it is going to be used more and more. And just to address another important question, a reason why I think people haven't used a lot of fiber composite in architecture is because there has been no series of standards in the IBC.
Right.
And recently, I would say as recent as 2016, now there's a chapter in the IBC for fiber composites. It still requires a lot of testing on your own, because when you make a fiber composite, you're making your own materials. This is one of the things I really enjoy about textiles, is you're constantly inventing with your own stuff. So you got to test that stuff.
Right.
But at least there's a process described in the IBC. And so I think your generation is going to have this available.
Well, or you do, I mean, we did the Continental Canopy project. We used carbon fiber, and we had to do our own testing to get it to pass. So you can do it, right?
Yeah.
And then, so the stiffener, I'm getting super technical here because I'm curious about, because the SOFTLAB and but this, there's a kind of intelligence or reactive condition that you've been working with, but also once it stiffens, then which is what you're working on in the origami piece, right? Then it kind of has that potential of strength, I suppose, right?
Yeah.
Right.
Yeah.
So, I don't know, we could open it up to questions here, so I'm not monopolizing, or, yeah. Rioni?
When you're teaching this material in the SOFTLAB, are you pulling students in from fashion and architecture? How do you start to share these skills with students who might only have architectural training?
Yeah, we don't have a school of fashion, but I would say the students that have come by SOFTLAB are from all over. We've had students, undergraduates from biology. We've had undergrads and grads from engineering, design come by. Usually because it's a space, people are curious, and they come by to look at it, and they see something, and we start talking, and then they get interested, and then we start working. I would say that has been one way of teaching. It's really informal because we're there working. Another way is I do offer a computational textiles course, but last couple of years, and probably this year as well, I'll be looking at carbon fiber composites, and students in architecture can sign up for that, as well as students from engineering. Haven't had any people outside of design take that course yet, but who knows? I don't know. There are some engineers that are working with nanotechnology at Penn State, and we have started talking about that. But, I'm actually about 5 years in at Penn State, and it took, I would say, 3 years to actually get the lab going, and then also get students in that were starting to work on projects. So now I think we're up and running. We've also applied to get an industrial knitting machine. So I think now we can actually start, doing some serious work with those guys. Yeah.
Talk a little bit about the psychospatial and how people might react to it in terms of their emotions, or people who may have difficulty expressing themselves. And so it's important that in terms of touch or what have you. Can you speak a little bit more about that? Because I was also wondering whether or not you had students from psychology who are sort of interested in exploring computational textiles as a way of exploring people's emotional reactions to space or to environments.
Actually, I haven't had any students from psychology, but that's a good idea. I should go talk to them. But one of the reasons I think this is hugely important is there's an article maybe 4 or 5 years ago in the New York Times Magazine where an author was describing his mother who could not communicate to anybody. She was in a nursing home, and someone gave her a small teddy bear, like made out of fabric, and as soon as she began to squeeze on that, it really started her neurons refiring, and she was able to gradually over time, over a few weeks, like communicate through that thing. And she was just kind of squeezing it. And so I thought about that, and I think that we've all had that experience where we might have been nervous, or we might have been worried or something like that, and taking a piece of fabric, or you're sort of playing with your sweater, you're playing with your hair, you're kind of comforting yourself. You're kind of like, letting yourself know that, you're here, this is where you are, this is what's happening. So I think that's a great idea. I should contact the psychology students and begin to work with them. I have to say that in architecture, emotion has kind of been pushed to the side. Like, people don't like to talk about it. They want to know, it's kind of something that there's not really defined either or to it either. It can be very nebulous, and I think that scares people off. But to me, that's the very thing that I love about it. That I think Palassma writes about this. I love that book, The Skin of the Eyes, that Palassma writes about this kind of connection with emotion through all our senses, and would love to drive computation in that direction, because I think there have been lots of computational works that really have to do more with counting, with vision, with kind of allowing architects to quantify and to kind of categorize things, but not so many that will allow us to reconnect with our emotions and how we can incorporate that back into architecture, begin to think about bringing that back.
It's interesting because, of course, you present your work very much also from the technological exploration, but there is the whole other side of what it looks like, what it feels like, the color, the shapes, the way you choose the specific size of a piece and how you make it out of these small units, the cream color of a lot of the things you make. And then in that video where you touch the piece over and over and over. So, going back to this other side that is instead more visual, more also about feelings, about warmth. I would be curious to hear a little bit, and the first thing that came to my mind as you started speaking, especially looking at the knit pieces, I was wondering how much this was also part of your history as a kid. There's something very playful also in the making of these things, and just wanted to hear also the more personal piece, maybe.
Yeah, definitely, you're right. I grew up with an aunt who loved to make things, and we used to, usually in the summer, she would come to visit, she would have vacation, and we would set up a couple sewing machines on the table, and we'd all get together. We'd go to the kind of sewing store, pick out materials and fabrics and patterns, and change the patterns, because she loved inventing things. We would sew and talk. So there's this kind of, for me, good memory of collaboration and talking with my family and making basically our summer clothes and making things for ourselves to wear. And in terms of the emotion, I would say that that actually having the tactility of having something in your hands is super important. Like, so the emotion doesn't just, it's not just there when you're in the building. It's something that if you're conscious of and you're thinking about through the kind of materiality of what you're making, it can be hugely important. And I hope that in architecture that we could bring some of this back. I know it's difficult because of just, I think, the history of our profession, how it's kind of set up, and also in computation, the kind of drive for visualization, which is hugely important. It's not that I am knocking visualization, but I think now that we kind of got some of that under control, like you were mentioning BIM, that we could have some other things that get put on the table. And so I think touch, smell, taste, a sense of heat. Touch is very complicated. I mean, it's really.
Thank you.
Thank you.
Terrific. Really interesting. Super. Thank you so much.